All right. So welcome to our lecture today. Uh, so since we have done our quiz very recently, maybe I don't have to repeat the root locus rules, right? So, but you can find the relevant information also on my webpage, where you get a brief summary of the root locus, mentioning that given an open loop transfer function, we are looking for the roots of ds plus k n of s, and writing down the rules, etc. I just want to ask if you have any questions on this website. I can answer now. Do you have any questions for your friends who have visited this site? And if you have any questions, I can try to explain further. If not, let's continue with our next topic. And that topic is related with one of your questions. So if a common question that I encounter in this course is that is the root locus technique used only for P controllers? Why? Because we assume that our open loop transfer function is in the form of k n of s divided by d of s, and that kind of assumes that there's only a P controller. And is this the only controller that we can use the root locus technique? I should say the answer is no. So you can use it for different problems as well. And the reason is that I will just simply write the definition that I use on my webpage for the root locus. So where is it? A second, please. Oh. Okay. Here. Okay. So as I said, so one can interpret the sketching the root locus problem as follows. So given the roots of n of s and d of s, could you plot the roots of d of s plus k n of s on the s-plane as k changes from 0 to infinity? Okay, so this is one interpretation of the root locus. Okay, so you can use the root locus technique. If you can formulate your problem in this form, then you can apply the root locus technique to any problem. All right, and I will show you one simple example for that. Okay. So let me start with an example. Suppose I have the following feedback loop. Here I have, let's say, s squared over, let's say, p of s. And let's say on the feedback path, I have, let's say, k times q of s, let's say, plus 2. Okay. And if p of s and q of s is known, okay, sorry, q of s is known, can you sketch the root locus for the closed loop poles? The root locus for the closed loop poles of the system. Of the system as k goes from 0 to infinity. All right, so assume that p of s and q of s is given like a regular polynomials of s. And let me start by writing down the closed loop transfer function. So what is the closed loop transfer function here? G closed loop of s is equal to, so it is g of s divided by 1 plus g of s. So it will be simply equal to s squared over p of s divided by 1 plus g of s h of s. So it's going to be s squared times k times q of s plus 2 divided by p of s. Okay. And if you multiply numerator and denominator by P of S, so you will have simply S square divided by P of S plus S square K Q of S plus 2S square, right? So what is the characteristic polynomial of this system? So it is the denominator of the closed transfer function, right? So a characteristic polynomial is simply P of S, so let's say plus 2S square plus K times S square Q of S, right? And the thing is that what I would like to do is that I would like to plot the roots of this equation, which is equal to 0, okay? I would like to plot the roots of that as K changes from 0 to infinity. So if this was given in this form, so let me say, if this was given in this form, let's say d bar of S plus K m bar of S equals 0. So I will assume that this m bar of S is the open loop zeros, d bar of S is the open loop poles, and I could have sketched the root locus for that, right? So notice that I can define this guy to be, let's say, d bar of S, and I can define this guy to be m bar of S, all right? Then I can write this equation in terms of d bar of S plus K times m bar of S, okay? Is that clear?
Yes.
Yes.
Perfect. So then if I treat this n bar and d bar as if like open loop zeros, and if I treat those as open loop poles, okay, and if I apply the rules of the root locus over here directly, I can sketch the root locus for that. I can sketch the closed loop transfer function pole locations with respect to as K change from 0 to infinity. Is that clear? Is there anything I can explain better here? Any questions? So you may think about your question why I'm writing the title of our next topic then. Okay. So our next topic is the
Hocam ben bir soru sorayım mı?
sure PID controller with root lock. So when I'm writing this, you can ask your question, please.
Biz bu d-bar ve n-bar tanımlamalarını yaparken closed loop transfer function'ı oturtmamız gereken bir standart form var mı, yoksa closed loop transfer function formundan bağımsız olarak bu tanımlamayı yapabiliyor muyuz?
So remember that we can formulate the sketching a root locus problem as this, like as follows. Given the roots of n of s and d of s, could you plot the roots of d of s plus k n of s on the s-plane as k changes from 0 to infinity? All right. So if you approach it in this form, so you can assume that this m bar of s is the open loop zeros, like d bar of s is the open loop poles, and then you can assume that I am finding the roots of this denominator here, okay? And that denominator corresponds to the denominator of the closed loop transfer function of our original system, okay? So it's already there. So this, what you are plotting is the roots of this equation, and this equation is the is given by the denominator of the closed loop transfer function. So if you are plotting the roots of this equation, you are plotting your closed loop poles here for this system. Huh?
Anladım sanırım. Bir tek numerator ile denominator arasında pole zero cancellation'ını yaptıktan sonra ki
You don't have to think about this for the time being, okay? So that you don't have to consider in this course, okay?
tamam, teşekkür ederim.
Especially in the root locus topic, okay? Because as you know, you can have these cancellations, but you should carry out them. But for the time being, you can neglect them, okay? Those conditions, okay? So let me continue with the PID controller with root locus then. All right, so our next example will be, so I will to describe this topic on an example. And so consider the case where we have the feedback system, sorry, plus minus, where I do have my controller here, GC of S, okay. And then you have your plant, let's say, G of S. And suppose you have a unit feedback system for the time being, okay? Something like this. And what I would like to do is that, so suppose I have multiple controllers that I can choose from, like a P controller, PD controller, PI controller, or PID controller. Okay, so let me write it down. Let's say this might be only one variable K, or it might be a PD controller K plus KDS, or it might be a PID controller K plus KDS plus Ki over S, okay? And I would like to see if I use any of these controllers, what will be the effect of that on my system by using the root locus technique. All right. So for the time being, let's assume that, let's start with a simple example, that G of S be equal to 1 over S plus 1 times S plus 2, okay? And let's start from the easiest case where we use a simple P controller for this system. And let's see how the closed transfer function poles, closed poles lay in the S-plane, where they lay as we change K from 0 to infinity, okay? So let me try to plot this S-plane. And let's assume that I'm using a P controller. So let me write that as like a P controller. Okay. And then in that case, this GC of S, so I can write it in blue. So this GC of S is simply equal to a single positive constant K, right? And I can write the open loop transfer function as K times G of S, right? So it is equal to GC of S times G of S, and that is equal to K times 1 over S plus 1 times S plus 2, okay? And it notice that it's in the form of K times N of S divided by D of S, okay? So I can plot this closed transfer function poles as K changes from 0 to infinity. Okay, so let's suppose that K is changing from 0 to infinity. And I would like to find the closed transfer function of the system and the pole locations, right? So let's start plotting the root locus by just first, let me put the open loop poles on the S-plane. So I have pole at -1 here. So I have a pole here, and I have another pole here at -2. Let's say here, so let's say -1 and -2 over here. So what is the number of asymptotes for this case? So it was the difference between the denominator and the numerator, right? So it is equal to 2. What is the angle of the first asymptote?
Pi over 2.
Exactly. So it is pi over 2. And what is the angle between the asymptotes?
Pi.
Exactly. So, and the angle between the asymptotes is equal to 2 pi over 2. Then that is also equal to pi. Okay. How about the intersection of the asymptotes with the real axis? So what is the intersection of the asymptotes? So that is equal to summation of poles minus summation of zeros. can go a little down. Oops, there's something from yesterday, so let me delete those. Okay. Okay. Divided by what? N minus m, right? So I have only 2 poles and I don't have any zeros. So the n of s is equal to 1. And what is the summation of poles? Minus 2 plus minus 1 is equal to minus 3. And I don't have any zeros, so it will be 0 divided by 2. 8 is equal to minus 3 over 2. Okay. So let's then continue plotting the root locus. So which part of the real axis is included in the root locus? So if I take a test point that doesn't satisfy the angle condition, so this section on the real axis will be included in our root locus, right? And let me also put the asymptotes there. So I will have the intersection of asymptotes at minus 3 over 2. So here is that point. And I will have 2 asymptotes there. One is pi over 2. The other one is minus pi over 2 or 3 pi over 2, okay? So the asymptotes will look something like this. If I try to plot in this way with the yellow color. So this will be my asymptotes, right? It will lay on this line over here. And as we already know, what's going to happen is that, so the root locus starts at the open loop poles and ends up with the open loop zeros or the asymptotes. So these 2 poles here will move towards each other, right? They meet at the point here and they will move following the asymptotes, right? So it will go something like this. So this is what happens when I'm using a P controller, okay? So as K changes to infinity, 0 to infinity, the closed pole locations move in this way. So let's have a look at some performance metrics that we defined for a transient response, okay? So we talk about, for example, steady state errors, we talk about settling times, etc. So let's investigate those concepts with the P controller, okay? So what is the steady state error to the step input for this for any system? We said that that is equal to 1 over 1 plus Kp, right? And Kp was defined as you might remember, we said that it is equal to, as s goes to 0, it is equal to the limit of the open loop transfer function. So what is the open loop transfer function? K over s plus 1 times s plus 2, right? And that is simply equal to, as s goes to 0, it is equal to k over 2. Then the steady state error is simply equal to 1 over 1 plus k over 2, okay? So what happens as k increases, what happens to the steady state error? So if k increases, the steady state error will decrease, right? So ESS will decrease. So that's a good thing. But when k increases, there's another thing happening here, which is undesirable. What is that?
Overshoot.
Exactly. So the overshoot is increasing, right? So the thing is that, so if you have complex poles, remember that, let's say somewhere over here, the angle, let's say I would call this angle as theta for the time being. When you have complex poles, complex conjugate poles, then you have underdamped response for the unit step input. And if theta increases, then the overshoot increases. If theta is too small, then you don't have much of an overshoot, right? So when k is increasing and increasing, your poles are drifting apart because they move away from each other. And then you have an increased overshoot, which might be very dangerous for practical systems, right? You would like to reach a desired input, but you exceed it with a very large margin that might not be desirable. Okay. And I can also ask you, so what is the best settling time for this system when I'm changing k from 0 to infinity? What is the best achievable settling time for the system? So remember that so Ts is equal to 3 over psi omega n, right? The real part of the roots. And if you have multiple poles on the real axis, the pole closest to the imaginary axis determines the speed of the system, right? So that determines the settling time, right? So when you start from k equals to 0 value and you start increasing your k value, when do you achieve the minimum settling time here?
When poles meet at real axis.
Exactly. So when the poles meet at the real axis, so the slowest pole will be still far away from the imaginary axis, right? So you will have 3 over 2. So it will be, let's say, 2 seconds. Okay. And so when you increase k further, what happens to the settling time? If the poles are moving on this line, okay, so the real part is not changing at all, right? So 3 over psi omega n is not changing. So after that point on, if you increase k further, you cannot improve the settling time, right? It will stay the same. It will be 2 seconds, right? Because the real part of the poles will be the same once they break away.
Yes.
Oh, okay, perfect. So let's continue with the PD controller then. So this is what we can achieve. We summarized what happens to those parameters when we use a simple P controller with a single parameter K. That's what we can achieve here. And that's what we inspect from the root locus. Let's try to use the PD controller, shall we? So I will write here PD controller. PD controller. And let's see what happens this time. Okay, so what is the transfer function of the PD controller? So you have a proportional term K and a derivative term KD times S, right? And I would like to write it down as my controller in this system over here, okay? And open loop transfer functions will be the same GC of S times G of S once again, okay? So notice that I can write this transfer function of the PD controller as follows. So I can take it into the KD parentheses. I can write that thing as S times K over KD. Okay. So in that way, what I can do is that I can say that this is okay, KD times S plus alpha. Okay. So I defined a new variable that will be my zeros, by the way. So that will determine the zero in the open loop transfer function. I call it alpha. The zero would be at minus alpha. And this is equal to K over KD. Okay. So what I can do is that, for example, if I would, I can by using a PD controller, I am introducing a 1, 0 and the K variable into the system, all right? And that alpha ratio I can keep fixed at the desired 0 location. For example, if I increase K by 3 times, I also increase KD by 3 times, so I can keep this ratio fixed, okay? Then I can have 2 degrees of freedom and 2 parameters to fix by introducing 1 0 location and 1 gain parameter that I will change from 0 to infinity, okay? So if I write down the open loop transfer function once again, it will be simply equal to KD times S plus alpha divided by s plus 1 times s plus 2. Okay. And this is equal to the PD control, right? So it is k plus kds divided by s plus 1 times s plus 2. Okay, so let's first investigate what happens to the steady state error to step input. Okay, so let me write down the steady state error to step input. It will be again simply equal to 1 over 1 plus kp, right? And kp is equal to limit as s goes to 0, k times kds divided by s plus 1. Let me write that k plus kds divided by s plus 1 and s plus 2. And that's again, once again, k over 2. Okay. So steady state error to unit step is 1 over 1 plus k over 2 once again. So this, we already know this, right? So we know that adding a derivative term does not change the steady state error, right? For the PD controller, change the ESS there. You also know that, for example, if you would like to change the steady state error, you need to change the type of the system, right? In order to change the type of the system, you need to add a pole at the origin, right? An integrator. That we will see in a second. Okay, so by just introducing this PD controller, we cannot improve over the steady state error, but we will have maybe other advantages over this transient response parameters like the overshoot, settling time, stability, etc. Okay. So if I go back to this open loop transfer function once again, so notice that I can write this thing as this is equal to kd times n of s divided by d of s. Okay, so I can keep alpha fixed and plot the close the poles when kd is changing 0 to infinity. Okay, so let me write that like so. Let's keep alpha fixed and change kd from 0 to infinity. Okay. So then I can plot the root locus for the closed transfer function. Okay, so let me do that. So I will plot the S-plane here first. Sorry about that. Okay, so let this be the real axis. Let this be the imaginary axis of my S-plane. So what are the pole locations here? It is -1 and -2, right? So this is -1. This is, let's say, -2. And I can put alpha wherever I want, all right? So I would like to place alpha as 0 in my root locus. So assume that this is a design parameter. Where would you like to put alpha, your 0? So let me ask once again. So we are adding a 0, okay? So we are adding a 0 to the open transfer function at -alpha. And 0 at s is equal to -alpha. And where should I put this 0, additional 0?
Origin.
For example, is it a good idea to put it over on the, your friend said origin or the right half plane? Is it a good idea to put it there?
If we put it to the right half plane, then the root locus extends to the right half plane.
Exactly. So remember that the root locus starts at the open loop poles and ends up with the open loop zeros. Okay. So as k goes to infinity, one of these poles is going to follow this to reach this zero, right? So if I, for example, put a zero over there, so this pole is going to move there, and when k exceeds a certain value, the system will become unstable. Okay. Or as your friend suggested, if you put it to the origin, so if k goes to infinity, it will be one of the roots will move to the imaginary axis. That is also will be very close to instability. All right. Also, you will have terrible settling times here, right? So the settling time of 3 over psi omega n values are going to be very large here when psi omega n is very small, right? So what might be a good idea to place our zero at? Where should we put that?
Can we put left of the leftmost pole?
Exactly. So the idea is that I can still put it over here, but again, one of the poles will be still close to the imaginary axis if I put the zero over here. When k is infinity, it will be still very close to the imaginary axis, somewhere between -2 and -1. And that's not going to improve the settling time very much, right? So we want the settling time as small as possible, at 3 over psi omega n value. So it might be as far, it is better to have it as far as possible, right? So it might be a good idea to put one of the zeros to the left of our two poles over here, right? So that when I'm increasing k, okay, one of the poles is going to follow this, is going to reach that zero, and the other one is going to follow the asymptote, by the way. What is the number of asymptotes here, by the way? So we added 1, 0 in the open loop transfer function. So the number of asymptotes is now decreased by 1, right? So difference between 2 and 1 is equal to 1. So it is equal to 1, and its angle is equal to pi, right? So the asymptote goes something like this, right? And as k, so as k starts from 0, these two poles are going to move towards each other, right? Because this part of the real axis is included in the root locus, right? And so they will move towards each other, and then they will break away, just like our examples in previous lectures, okay? And they will move symmetrically. Sorry about my drawing. And then, so let's say they will go this way. And then there will be a break-in point here where two complex poles meets on the real axis, and they will start moving towards the 0 and the asymptotes, right? So one of them will going there, it will go there, and the other one will follow the asymptote and will go there. When I'm changing KD from 0 to infinity. Do you all agree with that?
Yes.
Perfect. So this is the minus alpha point, okay? So let's say this is the minus beta point. Okay, let's say another color. So what I would like to ask is that what is the minimum settling time for this system? What is the best achievable settling time as KD changes from 0 to infinity? Zero settling time. So how can you say that?
If KD becomes
Infinity. So notice that if KD is going to infinity, one of these poles is going to this minus alpha. Right? And we said that the settling time is determined by the slowest pole, and slowest pole is the pole that is closest to the imaginary axis.
then the break-in point could be.
Exactly. So the thing is that if I say this is like 3 psi omega, then it will be simply equal to 3 over beta. So maybe I should say it in words, so or maybe I should write it. So to achieve settling time, okay, the closest pole to the imaginary axis should be as far as possible, okay? So closest pole to the imaginary axis should be as far as possible from the imaginary axis on the left half plane, right? Because, for example, at the beginning, I will have, at the very beginning, this pole is going to determine the settling time. At this k value, so this real part will going to determine 3 over psi omega settling time. And at that point, at the break-in point, the settling time will be equal to 3 over beta. And when I'm increasing k further, okay, so this time the slowest pole is going to be this pole moving here, okay, that pole is going to determine the settling time. And that will be worse than this 3 over beta. It will be larger settling time for that. Okay. And maybe I can also ask, for example, when does the maximum of the maximum overshoot happen? So for different k values, I have different, let's say, overshoot, right? And p value changes when kd is changing from 0 to infinity. So when is the maximum of this thing happens? So remember that if I have complex poles, I was looking at the angle theta, right? So if that angle is small, then I don't have overshoot. If the angle is getting larger, I have a larger overshoot. If this angle is 90 degrees, then I will have overshoot is equal to 100%. I have the undamped response, right? So the angle, the overshoot increases with the angle theta over here, right? So the maximum MP will be something like somewhere over here, all right? So, sorry, for that K value, if theta increases, then the overshoot increases. Let's say I reach theta max at this point, okay? And we have tangent to this circle, then I will have the maximum of the MP, theta max there. Let's say theta max, and that is set from the theta max there. Okay. But do you want to reach the maximum overshoot? We don't want the overshoot to be large, so we would like to avoid the overshoot as much as possible. So that values of KD values, we will have undamped responses with a lot of high oscillations. So I shouldn't stay at those KD values. I should either move further, I should move either increase the KD value or decrease the KD value to get rid of the oscillations there, right? Do you have any questions so far? If not, I will continue with the eye controller. Any questions?
Hocam, overshoot'un formülünü tekrar bir yazabilir misiniz? Şu an aklıma gelmedi.
Hatırlarsanız o kısayla ilintili bir şeydi. Cos theta'ydı, hatırlıyor musunuz? So remember that.
Tan theta diye hatırlıyorum ama.
Nope. So you would like to find the psi value first, okay? And then what you would like to do, you can see it also on my web page if you would like to. So maybe I can show you like this. I put it already there. So if you go back, so it changes with this psi over there, the damping ratio, right? And if you increase the psi, then the overshoot decreases, okay? And was equal to cos theta over there, okay? So simply, I think I plotted with respect to theta as well. So when theta is equal to 90 degrees, the overshoot is equal to 1. And if theta is equal to 0 degrees, then the overshoot is equal to 0, because both of these values are on the poles are on the real axis. Okay.
Okay, thank you.
Any other question? I mean, you can plot the overshoot in terms of psi. You can also plot the overshoot in terms of tan theta as well. You can also plot the overshoot in terms of theta itself, okay? And but remember that overshoot is related with the closed loop, so complex poles, right? For example, if you have poles over here, then you have the maximum overshoot. You have the undamped case, like you have sustained oscillations over there. It's never damping, and this angle is then equal to 90 degrees, right? And if you have poles over here, then this angle is 0 degrees. Then you have real poles. Then you have no overshoot. So it is related, and the oscillation frequency is the omega d over here, right? So you can maybe directly see the relation between the angle. Instead of psi, you can also use the angle here. It's more intuitive, if you ask me. Okay. All right. So let's continue with the eye controller then. So, okay, so let's say I'm not happy with this PD controller as well because I have overshoots, or I cannot improve the settling time beyond 3 over beta, and that might not be desirable in some cases. So let's try to use a eye controller and you see what happens there. So if I have a integral controller, the control transfer function will be simply equal to Ki over S. And then the open loop transfer function that we'll be dealing with will be simply equal to Ki over S times S plus 1 times S plus 2, right? So my first question is, what is the steady state error to step input?
0.
Exactly. So we changed the order of the system and we add a pole at the origin. Okay. Therefore, the steady state, we get rid of the steady state error. So it's a good thing. We managed to catch the desired step input. But what is the effect on the root locus there? So what is the number of asymptotes this time? I can switch to blue. So if this is the open transfer function, what is the number of asymptotes?
3.
Exactly, so it's equal to 3. And what are the angle of asymptotes? So it will be equal to pi over 3 minus pi over 3 and pi, right? And where is the intersection of the asymptotes? So it's going to be the summation of poles minus summation of zeros divided by 3, right? 3 minus 0. And what is the summation of poles? It will be equal to minus 2 plus minus 1 plus minus 0. And what is the summation of zeros? There are no zeros, so it is equal to 0. And divided by n minus m, which is equal to 3. So it will be equal to minus 1 over here. Okay. So, and if I sketch the root locus, it will be something like this, right? So when Ki is changing from 0 to infinity, let's see what happens with the eye controller. So let's have a look at the open loop poles. I have open loop poles at the origin. One of them is here. One of them is at -1 here. Let's say -1, and another one at -2. Okay. And we have the intersection of the asymptotes over here. So here we have the intersection of stone with the angles pi over 3 minus pi over 3 and pi. So try to put, so this will be our first asymptote. Okay. The other one is at pi over 3, so it's something like this. Sorry, I can do instead. This will be maybe easier. Let's see. That's something like this, right? These are the, okay, these are going to be the 3 asymptotes over here. And how is the root locus gonna look like? So first of all, let's have a look at the parts of the real axis that is included in the root locus. So the first part is going to be simply equal to this section will be included in the root locus, and that section will be included in the root locus, right? So this pole at -2 will follow the asymptote and will go to -infinity over there. How about those two guys? So those two guys are going to move towards each other, right? And then meet at a certain point, and then they will start following the asymptotes, okay? We don't know the exact trajectory, but we know the approximate trajectory of these poles. So what is the main problem here with the eye controller when you look at the root locus?
Stability.
Exactly. So if I increase Ki, all right, then the system may be unstable, right? So if I increase Ki, system may be unstable. And furthermore, I have terrible settling time, the overshoot, etc. But also this instability is the biggest issue there. Okay, so that's why you don't use eye controller itself. You usually use it with a P controller together. So you use a PI controller. So let's see the effect of that. Okay, so let me write down here PI controller. And lastly, we will also say the PID controller, but let's continue with the PI controller. The controller transfer function will be simply equal to K plus Ki over S for the PI controller, right? And I can write this transfer function as K times S plus Ki over S. And I can write it as in K parentheses S plus Ki over K divided by S, okay? So I can write this thing in the form of K times S plus alpha divided by S. And that alpha is equal to Ki over K, okay? So good news is by introducing a PI control, by using a PI controller, I am introducing 1, 0 to the system, one pole at the origin, and I have one free parameter I can change from 0 to infinity. So I can maybe write down the open transfer function and you can see it yourself. So it is equal to K times S plus alpha divided by S times S plus 1 times S plus 2. Okay, I introduce one pole and 1, 0 by using a PI controller. Okay, so let's try to sketch the root locus. So what is the number of asymptotes here?
2.
Exactly, 3 minus 1 is equal to 2, and their angle is going to be pi over 2 and minus pi over 2. Okay, and what is the intersection of the asymptotes? It's the summation of the poles minus summation of the zeros. So summation of the poles equal to 0 plus minus 1 plus minus 2 minus, and I have a 0 at minus alpha, so it is equal to minus alpha divided by 2, okay. And that is equal to minus 3 plus alpha divided by 2, okay. Perfect, so let's sketch the corresponding root locus then. Sorry, with a different color. So let this be the real line, and let this be the imaginary axis, okay. And I would like to place my poles on the S-plane. So I have one pole at the origin, S, and I have another one at -1 and another one at -2. And I will have 1, 0. So where should I put that 0? So, so once again, if you put the 0 close to imaginary axis, okay, then one of the poles is going to reach that 0. Then you won't have a good settling time, okay, if you put it over there. So it might be a good idea to put it somewhere over there. By the way, this is a design choice, right? So if you would like to put it over here, you can put it there. So there's no rule saying that you cannot put your 0 there. But the thing is that if you put your 0 there, then your settling time will be worse because the closest pole to the imaginary axis will be too close to the imaginary axis.
Peki tam sıfıra koysak hocam orijine. Pol zero cancellation olsa eksi birden eksi 2'ye gitsin.
That might be possible, but that will also, it is like, then it will go back to the P controller case, right? It's not using anything. So what you will have here is this thing you will plot here, right? So look at your open loop transfer function. If you do cancel those two, when alpha is equal to 0, then you will end up with a P controller. No, you are not using a PI controller then. And then,
Peki, teşekkür.
okay, then this P controller has its own problems that we mentioned, right? So let's have a look at this guy. So what is the problem with this guy? So let's first mark the section of the real axis that is included in the root locus, like this. And let's say we have the asymptotes over somewhere over here, the sigma, let's say somewhere over there. Its value is equal to -3 plus alpha over 2. So it's a function of alpha, all right. So, but let's assume that for time being, the intersection of the asymptotes is somewhere over here, okay. I mean, this point with the angles pi and the asymptotes at pi over 2 and minus pi over 2. So these two poles, first of all, the pole at -2 will go towards the 0. That will be the whole story for that guy. And these two poles are going to move towards each other and they will break away and then they will follow the asymptotes symmetrically. Sorry for my drawing, but this will be the symmetric paths with respect to the real axis. All right. So one thing is that what is the, again, the best settling time here? So first of all, we increase the order of the system. We fix this steady state error issue, right? So the steady state error to the unit step will be equal to 0. That's a good thing with the PI controller here. But another problem is that we still have these overshoot issues and the settling time issues, right? And another problem is that, so this 0 is at minus alpha, right? And suppose if I put this alpha too far away. So notice that the intersection of the asymptote is equal to -3 plus alpha over 2, okay? So if alpha is equal to 10, for example, it is +7 over 2. So this asymptote goes to the right half plane. And then the system will be unstable, right? So let me write it down. So as alpha increases, the asymptote might move to the right half plane, might move to the right half plane. Then that will cause also instability if you increase that k value over here, right? So let's try to use a PID controller instead. So let me write down the PID controller. And finalize our topic. So what is the transfer function of a PID controller? So I have a proportional term, so I have a proportional term, then I have an integral term, and I can write it closer. And I do have a derivative term here, right? So all of them. And I can write that transfer function as follows, right? So it is equal to kd times s squared plus k times s plus ki divided by s, okay? And I can write that thing further as kd parentheses, I can say that this is s squared plus k over KDS plus KI over KD and divided by S. Okay. So notice that I can keep this KKD ratio and KI over KD ratio constant to set a certain polynomial coefficients, and I can introduce two zeros in this way. So I can write this thing as KD times S plus alpha times S plus beta divided by S. Okay, and I can change the zero locations by arranging K and KD and KI and KD, okay, while changing KD from 0 to infinity. Okay, so in other words, we are adding with PID control, we add two zeros that we can place freely and one pole at the origin, okay, one pole. And this pole is at the origin, okay, so this is at the origin. And in that case, let's try to plot the root locus. See how it will look like. So suppose this is my S-plane, and I can stamp this axis. Okay. And let me place my pole locations. What is the open loop transfer function? Let me write that thing down. The open loop transfer function in this case is going to be GC of S times G of S. So it will be equal to KD times S plus alpha, S plus beta, divided by S times S plus 1 times S plus 2. Okay. So let me place my open loop zeros and open loop poles. So open loop poles at the origin, -1 and -2. And where would you like to place these open loop zeros? So again, you may want to put it somewhere away, right? So that the SK increases, the poles can be as far as possible from the imaginary axis. One might try to do that. So for the timing, let's put it one of them over here, one of them over there. Okay, let's say this is minus alpha, this is minus beta. And maybe I can also increase this, extend this axis a little bit further. Okay. And then let's try to plot the root locus for that. So which part of the real axis will be included in our root locus? So this part will be included, right? So that part will be included, and that part will be included. So what is the number of asymptotes? It's equal to 3 minus 2, 1. So there's one asymptote with an angle pi. So there will be an asymptote over here going towards this direction. And what's going to happen here is that, so that pole is going to this 0, right, as k goes to infinity. And these two guys will start moving towards each other. They will break away, okay? And they will follow a trajectory, and then they will break in. Okay. And if you increase k further, one of these poles is going to reach that 0. The other one will go to infinity. Okay. So in that way, if you increase k, the overshoots will decay. Okay, for in this setting, and you have two design parameters that zeros that you can put anywhere you want. Okay, and also you will be you get rid of the steady state error to step input, right? So maybe I can write that thing down as well. So just like the PI controller, the steady state error to the step input is going to be 0 with the PID controller, because the integral term take care of that. It increases the order of the system. And then in this setting, you don't have this danger of like increasing overshoot, like just like this. And maybe you should want to put this beta a little far away and alpha because for a better settling time. But you can design your zeros locations according to the system requirements as you wish. Okay. So do you have any questions? So we mentioned all the cases for the simple example. So P controller, PI controller, PD controller, I controller, and PID. So if you have questions, if I can explain anything better, please let me know right now.
Hocam, can you repeat settling time part?
Of course. So the thing is that
How does it change?
So the thing is that the settling time is determined by the pole that is closest to the imaginary axis, right? So for a small settling time, the pole closest to the imaginary axis should be as far as possible, right? And as you see over here, so the minimum settling time will be reached when this pole is moving this to this zero over there, right? So if those poles are passing over here, okay, or let me get another color and explain more clearly. So when k is equal to 0 at the beginning, which ones are the closest pole to the imaginary axis? So these two poles are the smallest poles, right? And if you consider this case, still these two poles are the imaginary, so are the slowest poles that will determine the settling time. Okay, but for example, when you take a k value where you have your closest poles over here, okay, and this guy is somewhere over here, so this becomes the slowest pole, right? That determines the settling time. And I said that for that reason, maybe you may want that beta value to be further away from the imaginary axis so that you're happy with that pole going to that beta value. Okay?
Hocam,
Yes, please.
bu
Anything?
alfa ve beta'yı eşit seçebiliyor muyum? Ve de şu break-in point'ine seçebiliyor muyum?
The thing is that you may choose them the same, all right? So you can put the double zeros over there, but the break-in comes from the equation, right? So let me have a look at that. So in that case, what you will have is this. So it is, you can imagine that this distance is being minimized in your case, right? So that these two become together. So this part is also included in the root locus.
Evet, daha da uzaklaşmış olacağız. Evet. Ki,
so you may choose any of these options. So you can also try to, for example, do a pole cancellation here as well. Like try to get rid of one of these poles if you want. So if it helps to your design parameter. So that is also acceptable. Good. Okay, if there are no questions for the timing, I can stop the recording.
I have a question.
Yes, please.
So from looking from here, we can see that like it seems like increasing KD is a good thing as much as possible, right?
Here, yeah,
Yes.
in the sense that, for example, this pole is going to move towards each other, and you won't have oscillations, and they will like go over there. Yeah.
Yes, but does it make sense to select KD like as large as possible? It doesn't seem to make sense for me.
The thing is that for the proportional controllers as well, sometimes you want that gain to be as large as possible. Of course, you cannot go to infinity in practical systems. Okay, you don't have such gain amplifiers with the infinite gain. Okay, But there might be cases where you like to design your system and you have to use some of the parameters at their maximum allowable value. Okay.
Okay, I see.
Not good point. All right, so I will stop recording right here. Thank you.